we are here today again to start we're just looking again at some of the byproduct and things that we get from the Riemann tensor. And today what we intend to look at is the Ricci tensor and also the Ricci scalar. So we have a Riemann tensor defined by this. Of course, these are partial derivatives with respect to x delta and with respect to s beta. And that is what we have. Now, of course, as we have stated before in one of our presentations, probably the last one, we could contract one of these, this and that. In doing that, of course, we intend to get the Ricci scalar. And that by doing that, the two scalars or two indices disappear, and what we're left with is halves of alpha beta. So what we just have to do is to set gamma equal to delta, or delta equal to gamma all over the place along the right-hand side. You can see this becomes a gamma, and this delta here also becomes a gamma. Okay, yeah, exactly, that's what we've got here. And also looking at this one here, this delta also becomes a gamma, and here we also have another delta, so that also becomes a gamma, everything else remaining the same. Yeah, but we've got one of the formulae that we have derived in some of our presentations in the past, where we could find an application for one of these, especially this one here. Whichever one actually, just the moment you have a Christoffel symbol such that only one of that is different from the other two, or doubly repeated index, or you can say two contracted indices in a Christoffel symbol. We have that here and we have that here too. So for instance, this, we had shown that this is equal to that, and when it is alpha, then it is equal to that. So it's simply equal to mean of the square root of minus g differentiated with respect to x mu. Of course, this is the same thing as, say, 1 over the square root of minus g, then that minus g dx alpha. So usually, all the alpha, the index here is usually the one here that is not repeated. The gammas are summed over and they don't appear on the right hand side. The same thing here, of course, happens with the mu here. The mu appears here, and the gammas also are summed over. So what we do this time around is simply to substitute this back into this expression here. So I have this halves of alpha beta to be equal to gamma, alpha beta gamma comma gamma minus ln of this. Of course, so what we've got here as a whole, that's this expression here, as you can see, is what we have here, and this represents the derivative with respect to alpha. But we already have another derivative here, a partial with respect to beta. So that is why what you have here now is a partial with respect to alpha followed by that of beta. Okay, now and then here also we have this, just as we have written it right from this place. This is the same thing as ln of the square root of minus g, comma, mu. And of course, everything else that we had before in the previous expression just follows us. Yeah, all that is left next is just some kind of manipulations. As we've got here, this is a minus sign, and this is a minus sign. We combine these two expressions together, this with the gammas. So what we've got here actually is, we could just make a transformation here. We could change the mu to gamma. But why would I want to do that? Because I have this derivative with respect to x mu, I have one with respect to gamma. First, I can do that because the mu is repeated. And why do I want to do that? I want to do that because I want to be able to combine these two expressions, or the two factors into a single factor of some derivative, such that I will just have to differentiate one. We shall see that shortly. And now this is minus that, minus what is there in the end. Okay, just like I was trying to show here, this ln of square root of minus g differentiated with respect to s beta, because that's what this means. So ln of the square root of minus g comma beta is the same thing as the ln of the square root of minus g dx beta. So this, of course, is just the same thing as saying, so working this out wouldn't be that too much of a big deal. So I've already started that here already. Now, if I were to differentiate this, of course, with respect to xg, or let me just do that already. I can just do that right away. That wouldn't be too much of a big deal. So let's do that here, since I can always clean and have a clean board now. So this is comma gamma, or comma beta here, sorry. So this is the ln of square root of minus g dx beta. And we said, of course, that this is same thing as just 1 over square root of minus g, the square root of minus g, the x beta. This is 1 over the square root of minus g times here, this is supposed to be the g, the x beta, the g, of course, we can see how that transformation goes. This, by the way, is going to be 1 over 2 times minus 1 times, okay, so let me say minus g with the minus half here. And so what we've got is 1 all over 2 square root of minus g, which is that, times the g here, the x beta. And what I've got here is, okay, so let me put that in bracket. This is that, and this is 1 over square root of minus g. And this is what we have. Of course, this multiplies that. And here I have got with me, oh no, I'm repeating this 2 twice, so sorry about that. I think if I'm going to include it here, I don't have to put it here. So I shouldn't have a 2 there. So what I've got here is simply minus 1 all over 2 times here the square root of minus g squared. That's what I've got there. Then the g here, the x beta. Of course, when I square this, I have minus 1 all over 2 minus g, the g, the x beta. The minus is cancelled. So that's why I have here 1 over 2g, the g, the x beta. So that's just what that gives me. Okay, now as for the first 2 terms I was talking about, like I've said, we changed the mu's here to gamma, and now we have this plus that. And you can see that this plus that will indeed be combined as this, because you can see if I were to treat this as a constant and differentiate this with respect to gamma, this is exactly what I will get, and the square root of minus g will cancel this, and that will just be the first term, plus. Supposing this time around I treat this as a constant, the usual Leibniz rule, and then differentiate this with respect to x gamma, and that's what you get. So in other words, the first 2 terms we have here could be combined into that. And so finally, what we have then is, coming back here, we have that the Ricci tensor f sub alpha beta is equal to just that, minus what we had here before, ln of square root of minus g comma alpha beta minus this. And then, of course, from here we can see it becomes apparent that the Ricci scalar, of course, the Ricci tensor is indeed symmetric in terms of the exchange of alpha and beta. There's no difference here if you interchange alpha and beta because the partials here commute. Of course, for the Christoffel symbol, the alpha and beta here, as far as they are the lower indices for the Christoffel symbol, is symmetric also with respect to that. Here, of course, you can see now, if I change alpha and beta, it's not much of a big deal because, as you can see here, I have a gamma, and I have a gamma. This is a dummy index. So I could as well change this dummy index, and also I have a mu and another mu. So I could, for instance, interchange gamma and mu. In other words, wherever I see mu, I put a gamma, and wherever I see gamma, I put a mu. So we usually denote that by that. And then also I do the same thing by saying, okay, perform the same interchange for alpha. Now, if I do this, this term remains the same. So in other words, the symmetry of the Ricci tensor is very apparent here. The Ricci scalar, of course, follows by the same procedure. Just again, at this moment in time, we just have to contract again alpha and beta by multiplying it with this metric tensor. And with that, it's just a simple procedure of multiplying the entire expression here with the metric tensor. And that gives us the Ricci scalar. So this is just one of the byproducts again that we could obtain or get, or of course, from the Riemann tensor. Now, we just want to give a feel again. Once again, some of the properties we could obtain of yes, of course, using some of the properties we've used here. For instance, the covariant derivative of this mixed tensor, beta. The usual thing, like we used to say before, differentiate the entire thing first of all ordinarily with respect to that. Now I want to contract the top symbol, so I'm going to have a plus, the Christoffel symbol. Let me use a delta or maybe a sigma just to try to conform with some of these dummy indices I see here. Sigma, I'm contracting it with the top index, so that is why I have a plus. Of course, beta will always follow me. What have I contracted? Beta, so it goes along again. And this is what I get here. Alpha, of course, remains where it is. Now, I want to contract a lower index. And that means my sigma will be on top here and C sigma will be here. What I'm differentiating with respect to beta will always be along the side. The alpha which I'm contracting, of course, joins this one, alpha. And then the beta that should have been here remains where it is, and nothing should change that. Of course, we can see already at this point in time that this is beginning to look like one of the things we used to have. We have a formula for that. Okay, for instance, we do know that in these cases we have beta, sigma, and beta. So beta is repeated. We said that this is the same thing as this. The x sigma, and here I have square root of minus g. Right? This is just what we get. And of course, here at this point in time also, we could decide to make some kind of changes. Whatever change that we feel will be more suiting to us. Yes, just before doing that, for instance, I can decide to make a transformation of saying that the sigmas here change. Okay, let me do that with beta. Yeah, exactly. Now, why am I doing this? Okay, first of all, I can do this because the sigmas here are dummy indices. Yeah, and so also are the beta. But again, why am I doing this? I'm doing this because I want the differential to be in terms of x beta. As you can see here, when the gamma is written in this form, beta is summed over and sigma is what appears in the differential. But in this form, if I make this transformation, it means I'm going to have, so let me write that in the second line first before I continue with what I had. So we had the x sigma, just remember that. So this becomes the C alpha beta, the x beta here, but then it becomes plus here, sigma, beta, sigma, C here. What have I got here? I've got here to be beta because I said I'm changing every sigma to beta, but then I'm changing every beta to sigma. So I have a beta here, two betas, and both have changed to sigma. I have sigmas here, and both have changed to beta. Finally, what do I do with this also? Just for the sake of argument again, because I'll be needing this in the end. So I would like to, for instance, in this case also make some transformation. Well, not too much of an importance at this moment. Let me just leave that the way it is until I feel the need to make any further changes. Sigma beta. But what have I made this change in the first place? You can see now that in this form, this is going to be equal to 1 over the square root of minus g, but d dx, instead of sigma, it becomes beta, square root of minus g. So you can see I have a dx beta here coming from this particular factor, and I have a dx beta here. Plus, you can see also that this is c beta alpha, c beta alpha. So that was why I had to make that change, or I decided to make that change, so that somehow I can combine these two terms. Looking at this then, it therefore means that C beta alpha dot dot beta, it therefore means that this is the same thing as the C alpha beta, the x beta, plus 1 over the square root of minus g, d dx beta. Here I have square root of minus g multiplied by C alpha beta minus. Here, again, I'm trying to say, well, one other thing we can decide to do also, just to make it look in line like with this, we can make an interchange. Well, alpha is not repeated, so we can't make any change really. Yeah, we can't. All we can do really is to make just leave it the way it is, because we can't. Alpha is not a dummy index, so we can't really change. So again, let's just leave that last time the way it is. So you can see that these two times combined is just the same thing as what we usually get, or we usually write just like here. This is the same thing as 1 over the square root of minus g, d, the x beta, combining the square root of minus g multiplied by c alpha beta. Then of course, we bring down the last term over there, sigma, sigma, beta. Yeah, of course we can see again, if we were to treat this as a constant, differentiate this with respect to x beta, the square root of minus g cancel. And then of course, if we decide again to treat this as a constant and differentiate, or to treat this as a constant and differentiate this, we end up with that. So it just means therefore that we could have shown this which was what we intended to do, of course, right from the beginning, to show that this is equal to that. The second one is more like what we probably have done before in one of these presentations. I can remember vividly. So, very quickly, let's just look into that. The second one again looks like this. This is C alpha beta. We have that to be that. Of course, the usual thing, so we have two contravariant indices. Differentiate the whole thing with respect to x beta. And then plus, again, because I'm contracting an upper index, what am I contracting with? Let me use some dummy index again, the sigma, because I see sigma repeated in the solution. So I have sigma. What I'm contracting is alpha, it moves here. This is beta. And then what have I got here? Beta. It means just where it is, I don't have to change that. Of course, this already looks like some contraction. This is again going to be plus. I want to contract here one of the top indices again. And what I'm using again is sigma. What I'm differentiating with respect to is some beta C. And what am I contracting? Beta. So I'm going to leave alpha exactly where it is. I'm contracting beta, so beta will be replaced by the dummy index, sigma. So beta is what I'm contracting, so it moves over here. Yeah, exactly. That's what it should be. Of course, one thing you can try to do is to simply pretend this is not beta, use some other index, perform the covariant derivative, and then just set it equal to the other beta. Now, I want to bring this close here. Again, because of my desire to make some combinations, I can decide to make this kind of transformation. Wherever I see beta, I change it to sigma. Wherever I see sigma, I change it to beta. That is possible because these two are both dummy indices here on this term. And why else again will I want to do this? Because, okay, fine. So you can see in the next step, this is the C alpha beta, the X beta, and that will be plus. Performing the interchange we're talking about, this becomes sigma, this becomes beta, this becomes sigma. C alpha remains what it is, but sigma becomes beta. Now plus here I have sigma. So just for the sake of argument here, okay, yeah, so just let's leave it the way it is. This is the term we're writing here, sigma beta. So, however, at this point in time, of course, we can see, and as to the reason why we had to make the transformations here, this is beta sigma. Again, using our old friend, this is square root of minus g, but then it has to be the x beta, the one that is not repeated, or the one that is not the dummy index. The x beta, and you can see, of course, it's the x beta that we have here. So this is one of the main reasons why we are doing that. So this therefore means that this covariant derivative might as well be written as 1 over the square root of minus g d the x beta, combining the two again. So this is a beta. This tensor analysis is a very tricky business because of the indices. You write a mu as a nu and it's all over, especially when you have a lot of algebra involved. So this is what we've got, multiplied by C alpha beta. I close that bracket, plus the last thing there, alpha, sigma, beta, C, sigma, beta. Of course, again, that gives us what we're looking for. And we can see that is just what we want. So I guess this was a mistake. That should have been C alpha beta. So you can see exactly this is what it means, combining these two terms. Of course, I will have put this here, and by the usual way, we've done this severally, so no need being redundant. And now, at this point in time, we can see we're saying consider the case for which C beta sigma is equal to minus C sigma beta. In other words, this case in which this particular object here is symmetric with respect to the interchange of these two. Again, so this is why I said I remember we did this somewhere in one of these presentations. And I'm very sorry if that was confusing at that point in time. Hopefully this will make it all clear. If we were to consider such a case, first of all, what we could do at this point in time is we could perform this transformation. Transformation of, say, sigma to beta. Wherever I see beta, I put a sigma. Wherever I see sigma, I put a beta. And if I were to do that, this would become here beta, sigma, C, beta, sigma. First of all, I can do that again because these two are both dummy indices. Having done that, now from what property we were given, this is the same thing as say minus gamma, beta, sigma, alpha, c, sigma, beta. Minus again because I interchanged these two. So that gave me minus. But the Christoffel symbol is symmetric with respect to the interchange of the lower indices here when it is written in this form. So in other words, this is the same thing as minus of gamma alpha, but sigma beta, c here, sigma beta. Now take note of this. This is exactly the same thing as the term we've got here. Gamma alpha, sigma beta, c, sigma beta. So these two, this and this is the same. In other words, we have been able to show that the entire object itself is equal to minus itself. And if that is the case, it therefore implies that this particular term here, c sigma beta, is equal to 0 for c sigma beta antisymmetric in sigma and beta. So unless you're given that property, you are not allowed to do anything else. This is all. This is as far as you go in this expression. You can't do anything else. If it is neither symmetric or antisymmetric, this term has to be there. But if it is antisymmetric, it means therefore that this term is 0. So for any moment or for any time when this is antisymmetric, it means that what we've got. So let me put that somewhere here and box it. So anytime C is antisymmetric, alpha, beta, then all you've got is this single term for this covariant derivative, the x beta, and square root of minus g C alpha beta. For C alpha beta antisymmetric. So that is when this expression reduces to that. So with this now, we are going to stop and look forward again to more other properties